So today's pre-lecture video, I wanted to concentrate on the fact that gravity is a vector and look at some individual problems where you have to use that fact. This will help you not only review adding vectors, but also getting used to how to deal with gravity. So in this chapter, we learned that through Newton's law of gravitation, there's a couple different facts that we need to know about gravity. In this picture, it's showing the fact that gravity is an attractive force. These two vectors here, this one and this one, are showing the force of gravity that the other mass is exerting on it. So here, for this force right here, this is the force that mass number 2 is exerting on mass number 1. Because it's an attractive force, it's pulling it towards it. Likewise, here, this force of gravity is the force that mass number 1 exerts on mass number 2. So the direction of the forces is because of the fact that it's an attractive force. And we'll look in a minute at how we calculate how large that force is. Notice when we think about the notation of these two forces that these are also an action-reaction pair. And as you can see, they're opposite in direction, and we'll also find that they're going to be equal in magnitude. So how we calculate the force of gravity, well, there's a couple different things that come into play. We've already talked about the direction, but the force of gravity is proportional to the product of the two masses, so the larger the masses are, the stronger the gravitational force is. It's also inversely related to the square of the distance between the particles. So as the distance increases, the force of gravity will get weaker. Another thing that we want to talk about is this gravitational constant. The gravitational constant, which is found in all the expressions for gravity, is 6.67 times 10 to the minus 11, and the units would be newtons meter squared per kilogram squared. And it's easy to know that because we know that when we put in the masses and the radius, we're going to get the units of Newton because it's a force. Notice that this is a small number, and so that means that gravity is a weak force. We don't really think about it too much, but everything that we learn about gravity, we realize that we actually then should feel a force of attraction with any mass that's near us, but we know that we never really are affected by that except for when the one mass is the mass of the Earth, which is very large. But the fact that this constant is very small explains why we don't also feel the forces of attraction that must exist between all the masses that are around us. All right, so let's use the idea that we know how to calculate the force of gravity, and we also know that it's an attractive force. Now, what if I was given two masses? Here's one mass, and here's another one. And I'm just going to say that one is 3 times as large as the other. The total distance between the two masses we're going to call L. And basically then the question is, where should I put another mass, a third mass, so that it feels no force? To help me out, I'm going to call this mass number 1 and this mass number 2. And basically I have 3 different places where I could place my other mass to see if it feels no force. I could put it to the left of the small mass, I could put it to the right of the larger mass, or I could put it somewhere in between. So let's sort of test that out. If I put the mass right here, what I want to do is I want to figure out the direction of the two forces that mass m and 3m would exert on this mass over here. They have to be in opposite direction in order for them to ever cancel out, and that's what I'm looking for. Because the force of gravity is an attractive force, I see that the smaller mass would exert a force to the right, and I'm going to call that F1. But I also see that the larger mass would also exert a force to the right, and I'm going to call that F2. Well, those two forces are in the same direction, so they can't cancel out there. And if I put the mass over here, I can see that, again, my two forces, the force due to mass 1 and the force due to mass 2, are also going to be in the same direction because of where everything is oriented. So finally, I'm going to try the mass in the center. And here, then, I see that the larger mass, 3m, is going to exert a force to the right, but m, the smaller mass, is going to exert a force to the left. Now I know that this is the only location or the only region where the forces could cancel out. The next thing I need to figure out is exactly where would I put it. So I'm going to just call this distance between here and here x, and then the distance between the mass and the 3m mass will be L minus x. And I want to set F1 equal to F2 when I'm just talking about the magnitude of the two forces. For F1, it would be big G m times m over x squared. For F2, it would be big G m 3m over L minus x squared. And so that's how I'm going to set the two masses equal to each other. The two forces equal to each other to figure out where x is. Notice that the mass in the middle actually is present in both expressions, so it cancels out. So it turns out it doesn't depend on m, at least the mass that I place in the middle. It doesn't matter how big that is, it's not going to affect where I have to locate it to feel no force. I'm also going to get rid of this other m, which is common in both terms. And then I also can get rid of g. Then to find it, I would cross multiply. I'd have L minus x quantity squared is equal to 3x squared. I could use the quadratic formula to figure out what x is. And what I should find is that x is going to place this mass a little bit, it's going to be closer to the smaller mass and further away from the larger mass in order for those to all cancel. Alright, so we figured that one out. Let's look at this example. Now here, this is similar, but we're going to actually do the calculation where the forces actually aren't equal to each other, and so we'll see what the net force is. So we have two masses, one 5 kilogram mass and a 10 kilogram mass. And we want to find the net force on a 0.1 kilogram mass that we place in between them at the distances given. So again, I'm going to call this mass 1 and this mass 2. So mass 2 is going to exert a force towards it, to the right, and mass 1 will exert a force on the middle mass to the left. And so the next thing that we will do is we would figure out how large each force is. Now, we've already drawn the direction on the picture. We don't need to put any negative signs in when we do the calculation. We're just going to remember that one force is to the left and one is to the right. So we have m1 over r1 squared, because we'll call this r1, and this is just going to be m. And so this turns out to be 6.67 times 10 to the minus 11. That's the gravitational constant. The mass in the middle is 0.1 kilograms. The mass to the left is 5. And the distance is 0.4. And we have to square that. And so this turns out to be 2.08 times 10 to the minus 10 newtons. Notice how it's a small number. Force 2 is equal to G m m2 over r2 squared. We're calling this r2. So that's 6.67 times 10 to the minus 11, 0.1 times 10 over 0.6 squared. And that turns out to be 1.85 times 10 to the minus 10 newtons. All right, so that's the magnitude of the two forces. We'll go again. F2 is to the right, F1 is to the left. The total force is going to be equal to the F2 minus F1, which which would be, when we add the two forces together that we calculated, it's actually minus 2.27 times 10 to the minus 11 newtons. So the net force acting on this mass is to the left. All right, and that's how we would use the vector notation. Now, the last one I'm going to do is something a little bit more involved because it's going to use x and y components. So in this example, we're going to imagine that we place a mass of 0.015 kilograms at point P, and we want to find the total force acting on it due to these other three masses. So again, I'm going to label them. This will be 1, 2, and 3. And so the first thing that we always do is we draw the direction of the force. So this mass is going to pull it towards it, and so that will be the direction of F1. This is going to be along the diagonal because it's always along the line joining the two masses. And so mass number 2 will pull the mass in that direction. And then finally, mass number 3 will exert a force on it that's going to be to the right. So we first use the idea that the gravity is an attractive force to draw the direction of our vectors. Then we want to figure out how large those forces are, and we'll add them as vectors. So one of the things we might notice is mass 1 and 3 are actually the same mass, and they're also located the same distance away from the mass that's at point P. So we could actually right away realize that F1 is equal to F3. And that's going to be equal to G, the mass at P, times those other masses, 1 or 2, it doesn't matter, over 0.5 squared. So this is 6.67 times 10 to the minus 11 times 0.015 times 1 over 0.5 squared. And so that actually turns out to be 4.01 times 10 to the minus 12 newtons. And then we can find F2. F2 is going to be equal to G, the mass at P, times mass 2, over that distance squared. R is going to be the square root of 2 times 0.5. So we can figure what that is. So it's 6.67 times 10 to the minus 11 times 0.015 times 2, and then the square root of 2 times 0.5, all that squared. This actually turns out to be 4 times 10 to the minus 12 newtons. So we have those pieces of information. Now we're going to have to add these as vectors. So let's just write these down again. F1 is equal to F3 is equal to 4.01 times 10 to the minus 12 newtons. And F2 turned out to be 4 times 10 to the minus 12 newtons. Now, I want to find my net force. First, I have to find the net in the x direction, which is going to be equal to F3 plus the x component of F2. So it's going to be 4.01 times 10 to the minus 12 plus 4 times 10 to the minus 12 times the cosine of 45 degrees. Because this was a square, that angle is 45 degrees. And that ends up to be 6.83 times 10 to the minus 12 newtons is the x component. The y component is equal to F1 plus F2y, which is 4.01 times 10 to the minus 12 plus 4 times 10 to the minus 12 times the sine of 45. If you remember things about sine and cosine of 45, you're going to remember that this is actually going to give us exactly the same value as the x component. So the total net force, we use a Pythagorean theorem, is 9.66 times 10 to the minus 12 newtons. And the angle is the angle whose tangent is the y component over the x component. Well, the x and y component are the same, and so our angle, we should see, will turn out to be 45 degrees. And so these are just some examples of how we sort of combine our knowledge of vectors with this new information about how we calculate the force of gravity.